Alright, so in this video we're going to go back over the main concepts that you see with gas laws and also some stuff with solutions. So first of all, when we talk about a gas, it is compressible. Basically, you have a lot of space in between those molecules, so you can compress them into a smaller container. They also have no definite shape or volume because they just fill the container. They will occupy more space than solids or liquids because they keep moving around. They're basically going to fill up the space of whatever they're in. The collisions on the container result in pressure. So that's why when we talk about gas laws, there's pressure involved because those particles are going to be hitting the walls of the container. They have low densities. And then at STP, so standard temperature and pressure, which is 1 atmosphere pressure and 273 Kelvin, which is different in thermo, 1 mole of any gas is equal to 22.4 liters. Alright, so just a couple of things that we need to keep in mind when we're talking about gases. Well, the kinetic energy of a gas is directly proportional to the temperature in kelvins. So if you have a higher temperature, you're going to have a higher kinetic energy. And basically, if you look at the equation for kinetic energy, that's equal to 1/2 times the mass times velocity squared. Well, if you heat up something, so if you add heat energy to it, the velocity is going to be faster. The speed of the molecules will be faster, which leads to a higher kinetic energy. Now, gas particles, when you compare them to the actual container that they're in, those gas particles actually only take up a very small amount of space compared to the container. So we say that they take up a negligible amount of space. They also will constantly be moving, and it's always random, and energy is not lost in their collisions. So even if they hit the wall of the container, they should still have the same amount of kinetic energy after the collision. And then also, and this also is in reference to when the gas molecules hit each other. Now, gas particles do not attract one another, so basically there should be no intermolecular forces when we're looking at these gas particles. All right, so the speed of gases. So if we are looking at a graph like this, we're basically, this is called a Maxwell-Boltzmann distribution. Basically, all the molecules are technically moving at different speeds, but we take an average. So we're basically just looking at the peak of this line to get the average speed. So if I'm looking at O2 at 25 degrees Celsius versus 1,000, well, at 1,000 degrees, the average is about 800 meters per second, and then for 25 degrees, it's about 400 meters per second. So this shows that as I increase my temperature, the speed of the molecules will increase too. All right, so speed is also impacted by molar mass. So basically, the heavier the molecule, the slower it's going to move. The lighter the molecule, the faster it's going to move. So if I look at this diagram, helium has a mass of 2. Oxygen has a mass of 32, so it's the heaviest one here. Well, oxygen has a lower average speed compared to everything else, and then helium would have the fastest speed. And now this is provided that they're all at the same temperature too. So mass and temperature both impact speed. So if you increase the mass, you're going to decrease the speed, and if you increase the temperature, you're going to increase the speed. All right, so if I change the temperature, I will change the velocity, which will change kinetic energy. Temperature is the only thing that's going to impact kinetic energy. But you would say, oh, well, what about mass? Mass makes a molecule slower or faster too. Thing is, even if I were to change the mass, that would impact the velocity. So if I made m higher, v would get lower, and vice versa. So kinetic energy will not change. The only thing that will change kinetic energy is the temperature. Okay, so if you're going to compare two different samples of gases at the same temperature, the kinetic energy is the same. This is a very important concept because it comes up on every single AP exam I've seen. And a lot of people will miss it because they get speed and kinetic energy confused. The only thing that impacts kinetic energy is temperature, and that is it. So if they're the same temp, same kinetic energy. All right, so effusion and diffusion also happen with gas molecules. So effusion, I like this diagram, shows basically if you were to have a balloon and pop it, like put a small hole in it, the gas molecules will escape through that tiny hole. That's called effusion. So eventually they escape out, and then you don't have a balloon anymore. Now diffusion is when you have a gas and it spreads throughout the entire room. So basically if somebody decides to spray something, and it's not always a pleasant smell, everybody has the luxury of smelling it though, because the gas molecules will spread out throughout the room, which is why this person's running. So smaller particles will effuse and diffuse faster. That makes sense. If you have a smaller particle, they will move faster regardless. So if we're moving through a tiny hole, or if we're spreading out to fill a space, it's going to happen faster. All right, so let's look at 3 containers. They're filled with equal volumes of O2, CO2, and N2. All of the containers are at the same temperature and pressure. Okay, so which container has the smallest mass? Well, they're all at equal volumes. Then we just need to look at the mass for this. All right, so O2 has a mass of 32, CO2 is 44, and nitrogen is 28. Well, the smallest mass should be N2. All right, so which container has the greatest velocity? So temperature and mass both impact velocity, but they're at the same temperature, so I'm looking at mass. So the lighter molecule will have the greatest speed, or move faster, so N2. Which container do the gas particles have the greatest kinetic energy? Well, the only thing that impacts kinetic energy is the temperature, but they're all at the same temp. So technically all of them have the same kinetic energy. All right, and which gas would leak out the fastest out of a whole of a container? So which one would effuse faster? That one, again, should be the smallest. And I could have also asked which one would have the slowest velocity, and that would have been carbon dioxide. Or I could have asked which one would leak out the slowest. That would be carbon dioxide. I could also have a question, hold on. I could also have a question like this, where I have a container, I have a little hole, and I had all of these gases in there. I have O2, CO2, and then also N2. And they could ask, at the end of an hour, what would be in the container the most? Well, the thing that effuses faster would go out first, and then the O2 would be next, and then CO2. So at the end of this hour, or how much ever time has passed, I would have more CO2 in that container than anything. All right, so let's look at the relationship between volume, temperature, moles, and pressure. So you have a few laws. You don't need to associate the names with the laws. You just need to know the relationship. So Boyle's law says that pressure and volume are inversely related. So as one goes down, the other one goes up. So basically, as I increase my pressure, my volume should decrease. And think about a syringe. If I increase the pressure of that syringe, I'm making the space for the gas molecules very, very small. Okay, so if you know that, then you should be okay. But knowing this, they could also ask you a question which might involve you halving the volume. So then what happens to the pressure? Well, if you half the volume, then that means that your pressure would go up by 2. So if the pressure of the volume is halved, the other one would go up by 2. if the pressure of the volume were to go down by a factor of 3, the other one would go up by a factor of 3 as well. So if one goes down by 3, the other one goes up by 3. All right, Charles' law deals with volume and temperature. So as I increase the temperature, the volume should increase. Think about a balloon. If I heat it up, the gas molecules will start to spread out and the volume of the balloon will go up. Avogadro's law deals with volume and moles. Again, it's a direct relationship. So if I have more molecules, I'm going to have a larger volume. Gay-Lussac's law deals with pressure and temperature. It's a direct relationship. So as temperature goes up, pressure should as well. That's why they tell you not to heat up aerosol containers. Now, if any of these factors change, the other factor will change by that much as well. So if I were to increase my number of moles by 3, my volume would increase by 3. And that applies to all of these variables here. All right, so the ideal gas law is the one that we typically see and use. It's PV equals nRT. So if you're reading a problem and it gives you a pressure, a volume, it mentions temperature or moles or grams, if it's all mentioned in the same problem, it's probably going to be an ideal gas law problem. So sometimes they might tell you that it's at STP. If they do that, that means that you're at 1 atmosphere pressure and 273 Kelvin. So this could be giving you 2 of your variables if they tell you that. You're going to use the gas law constant that matches your variables. Typically it's this one, but when you plug it into this, make sure your volumes in liters, your pressures in atmospheres, you have moles, and you have temperature in Kelvin. So when you're using this equation, you need to make sure you watch what substance they're asking for and which substance they give you. So they might give you a number of moles, or they might even give you a volume of something, but then ask for one of the variables of a different substance. So if I'm looking for, let's say, pressure or volume of carbon dioxide, I better make sure my moles are of carbon dioxide. But they could also give you an amount of aluminum or something else in the reaction. So you might have to do a combination of stoichiometry and the ideal gas law. You have to make sure if you use this, it's the same substance that you're looking for. All right, so Dalton's gas law is also another important concept. Basically, if you have a mixture of gases, the total pressure is equal to the partial pressure of each gas combined together. So if you have number of moles of one gas, you can solve for the partial pressure of that gas using this. A mole fraction can also be used to determine the partial pressure. So the mole fraction is equal to the number of moles of A divided by the total number of moles. So let's say that I have 1 atmosphere of pressure in a container that has, I don't know, 1 mole of O2 and 2 moles of N2. And I want to know the pressure of each gas. I can use the mole fraction. So for O2, it would be 1 mole of O2 divided by the total, which would be 3. And then I could multiply that by my total pressure and get the partial pressure of O2. Do the same thing for N2. All right, so one of the things or ways that you might see Dalton's law applied is if you are doing an experiment and you're collecting a gas over a liquid. So, and this is typically happening in experiments if we're collecting a gas, because water displacement is the easiest way to collect the gas. All right, so if you do that, what ends up happening, so if I were to have this mixture right here, the gas is being generated in this, it's going out through here, and then basically the gas molecules will go into this container and push the water out. Well, while this is happening, some water molecules are actually escaping. Some of those are escaping into this little space. So some of the water molecules actually vaporize. So we have to account for the water vapor in this container along with the other gas. So let's look at an example where we might see this. So right here, let's go ahead and start pulling out our variables. 41.5 is our volume, and this is of nitrogen gas. All right, it's collected over water at 23 degrees Celsius, so temperature is 23 degrees Celsius, and I already know it's gases, so I have to convert this to Kelvin. So 296. And it also tells me that the total pressure is equal to 775 millimeters of mercury. I need to calculate N of nitrogen. All right, so I know this is ideal gas law, mentions all of the variables. All right, so if I were to do this, I have total pressure. Well, I can't do that. I can't put that in there because in this container, I not only have nitrogen gas, but I have water vapor. So I have to get rid of my water vapor here. Then I can go ahead and do my equation. So first thing, if I look at R is equal to this. I need to make sure everything matches this too. And also, I still have to subtract out my water vapor pressure. Well, that's in atmospheres. So I'm going to have to convert this. And if you look at your reference sheet, there is a conversion between millimeters of mercury and 1 atmosphere. That's on your reference sheet. So I get 1.019 atmospheres. Well, this is the total. I still need the pressure of just nitrogen. So that's going to be equal to the total pressure minus the pressure of the water vapor. So when I do that, I get 0.992, or roughly. All right, so I have my pressure of nitrogen now. Everything is converted to match this, so now I can just plug it into my ideal gas law. So P is equal to this, not the total pressure. Volume is 41. N is unknown, that's what we're solving for. And my temperature is 296. All right, so when I solve for this, I'm going to get my N, which is 1.69 moles of nitrogen. All right, so anytime that we collect a gas over water vapor, you need to account for that water vapor pressure. So remember, the total pressure is equal to the pressure of each gas added together. All right, so a mixture of 43.2 grams of oxygen and 21.1 grams of carbon dioxide are contained in a vessel. Exerting a total pressure of this, find the pressure of each by each gas. So we're given a total pressure here, which is 980. And we're also given an amount of oxygen and an amount of carbon dioxide. All right, so if I want the pressure of each gas, I need to get the mole fraction. So I have to convert these to moles first. So 1 mole divided by 32 grams will get me 1.35. 1 mole divided by 44 grams will get me 0.502. All right, so now I've got the moles of each compound. I need to get the total moles. So 1.35 plus 0.502. And essentially, I'm basically finding a percentage here. That's what a mole fraction is. It's just a percentage. So that's 1.852. So now that I have that, I can multiply my mole fraction by the total pressure. So for O2, my mole fraction will be moles of O2 divided by my total moles multiplied by my pressure. So that's going to be 714 millimeters of mercury. It didn't specify the unit, so I'm just going to leave it in what it gave me. All right, let's do the same thing for CO2. Moles of CO2 divided by this times my total pressure is 266 millimeters of mercury. All right, so something else that's pretty important are deviations from ideal gas behavior. So gas particles are typically very far apart from each other. They don't interact with each other. This is ideal. So that means that if I were to calculate a pressure or volume using the ideal gas law, the calculation should match what I measure, okay? That doesn't always happen though, because if the temperature is high, the pressure is low, the molecules are not attracted to each other, I'm going to see the ideal behavior. But what happens if temperature is not high or pressure is not low? So if I increase the pressure and decrease the temperature, well, if I do that, the gas molecules are going to be closer together. If I increase the pressure, I'm putting them closer together, and then also if I decrease the temperature, they're going to have less kinetic energy and they start to move closer together. So once that happens, they're interacting more. The volume, because they're closer together, is going to be lower than expected. So if I go calculate a volume and then I measure it, when I compare it, I'll see that the volume is actually lower than it should be. Now, if molecules are attracted to each other, they're going to be closer, and then that volume is going to be lower than expected again. But because they're attracted to each other, they're not hitting the walls of the container as much. So that means that my pressure is also going to be lower than expected because they're not colliding with that container. So this also includes larger particles, because if we have larger particles, they have a stronger London dispersion force, so they're interacting with each other more.